Okay, we're going to begin with the following experiment or thought process. Let's say that we have a wall, and behind the wall all we have is water. Okay? Let's say that then we, magically cause this wall to disappear. If this wall disappears, the water is going to essentially flow, right? Such that what we will get at the end is essentially a puddle of water. There would be no slope, it would just be water resting on the ground surface, right? Now, what happens if we do the same, but in the case of soil? So if we have soil behind a wall, and all of a sudden we cause the wall to disappear, yes, the soil will basically move towards the mudline side, but what you will get is a slope, right? So the soil will not float towards a flat configuration. There will be a slope left behind. So what this tells us is that, clearly, we expect this, right? Water is a fluid. Soil is not a fluid, even though it actually acts somewhat like a fluid sometimes. Okay? It's a particulate material. Which means that it is made of particles, obviously you know that. So what I'm trying to say here, or the key of this, is that the soil has a capacity to sustain itself at some angle, unlike a fluid. This is because as a particulate material, soil can sustain shear stresses. At a given point, on given planes, there are shear stresses, tau. These are supported by friction. The shear resistance of a soil or any particulate material comes from the frictional resistance between the particles and the fact that the particles may have to climb past each other for that stress tau to be surpassed. In any case, the difference is very clear. A fluid cannot sustain a slope, whereas a soil can. So when we present the system with a wall, let's say, what we are really doing is we are helping the soil stand at 90 degrees. The soil can stand at some angle, but we know that if we place a wall, we can allow the soil then, or help, let's say, the soil to come up to 90 degrees. So this angle here is the one that can be supported by the wall. This angle here, so to speak, is the angle that can be sustained by the soil itself. So the soil supports itself up to here, and then we allow it or help it to support itself up to here with the use of a wall. Okay, this concept is very important because it basically leads to what we're going to talk about next. Okay, we're going to call this little section here the K0 section. K0 is a big K with a little 0 subscript. All right. Let's say that we have a wall. Very simple, no footing. This is just an idealization so that we can understand what we are doing and where we're going. Okay, so what I'm going to do is I'm going to take a point located somewhere in the backfill, but close to the wall. Okay? And what I'm going to do is I'm going to draw, or I'm going to denote graphically the stresses at this point. Okay? This point has a stress that acts vertical stress, a stress that acts laterally, horizontal, right? And there's stresses all around the point, okay? And those are denoted, all of them, including these two, are denoted by the Mohr circle. So if I draw a Mohr circle for this point, we are going to be able to describe all of the stresses that it feels. Okay, so let me just do it here with my little, just a second. Here we go. This is an easy way to draw a circle. Great. Okay, so the vertical stress is higher than the horizontal stress, right? And basically we have our circle that denotes all the stresses that act at this point. This is the circle, point A. Good. Okay, now, where do I do this? Let's say here. Remember the lateral stress ratio from your undergraduate geotechnical engineering course. The lateral stress ratio is the horizontal stress divided by the vertical stress. Okay? So if we take this value and we divide it by this value, we get K. This is the K that you all know. Now, why did we call this K naught, or K sub 0? The reason we did that is because K can actually vary. The K that you probably know, the only one that you know, is the one that is actually K naught, is the one associated with no movement. In fact, is the one associated with this problem. You have a profile, rock, soil, here's a point, right? If you want to know the horizontal stress at this point, you get the vertical stress multiplied by K. There's no movement here. This is a geostatic condition with no construction or walls or excavations or anything. This is at San Diego State, for example, the CV 462 effective stress analysis that you did, okay, in 462. So in this case, the K that you use is actually K naught. And for this case right here, it's also K naught. And here's the Mohr circle for the point. Okay, all good. Now, in reality, what happens is the following. Because you have soil in the backfill side, and you don't have soil in the mudline side, the soil here is pushing the wall out. There is a force by which the soil is pushing the wall, or that the soil is using to push the wall. The wall is a structural system that is a real system, and therefore when it feels a force or stress, it deforms. It responds to that force. So in all real conditions out there in the field, if you walk around where you live and find walls acting everywhere, supporting backyards and front yards and anything else, you have to know that those walls are under stress. Therefore, they are deformed, just like every structural member in the building that you are inside right now. So the way that a wall deforms by that force, there's different ways, but the most common are there's two most common ones. One is the slight rotation of the wall, and the other one is a slight sliding of the wall out. Now, when I say slight, it means very small, right? So a wall that is, for example, 2 meters high may respond to this force of the soil back here, acting laterally, by moving out maybe, I don't know, a few millimeters, 2 or 3 millimeters, okay? Now, this is the real case. That's what's really happening, and that's how walls are operating and properly in the field. So what does this do to a Mohr circle? Okay, well, let's go back before we mention this or describe what happens. Let's go back and realize that when we did this, when I drew all this stuff here, I was under the assumption that the wall was remaining static. It wasn't moving due to that load that we now know exists. Therefore, if the wall doesn't move, then this case and this case are the same. They are geostatic. There's no wall movement, therefore this case is the same as this, and the K that is relevant is K naught. Now, we now know that the wall actually, all walls move out a little bit given the force exerted by the backfill? Well, let's do an exercise. Let's say that you stick your finger in here, okay, at point A. Let's say that after you stick your finger in the point A, the wall moves either out by sliding or out by rotating at the top. Basically rotating about this point, moving like that, rotating out a little bit. So what would happen to the stresses? Well, if you think about it, if you have your finger in here, the vertical stress as the wall moves out will remain the same because there is the same amount of soil over that point. But intuitively, you should realize that if the wall moves out, the lateral stress would be relaxed a little bit because now there's more space for the soil to kind of accommodate laterally. So what happens to the Mohr circle as the wall moves out is the following. Mohr circle becomes bigger. How? Well, the vertical stress remains the same, but the horizontal stress starts reducing as the wall moves out. It goes like this. The wall moves out a little more, goes like that. Notice that the horizontal stress keeps on getting smaller and smaller. Okay? Now, here's where we have to bring something else in. Here we say the following. Look, in the Mohr circle space, we can denote the stresses acting at a point, drawing the Mohr circle, right? We've drawn the Mohr circle at rest, which is the one corresponding to K naught. This is called at rest or no movement, right? Geostatic, let's say. However, you can see that the Mohr circle is changing, right, as we do stuff to the system. In this case, the stuff is move the wall out or allow the wall to move out a little bit just because the soil is pushing it. So that's this world, and that's the Mohr circle in its world. On this plot, we can also draw the line that denotes the strength of the soil. Any point in the soil has a strength denoted by this line. The strength is equal to sigma prime tangent phi plus C prime. Here I've chosen the C prime to be 0, and I'll explain later on why. Okay, so now we have two things drawn in the same plot. The Mohr circle, or circles for this point, and the strength envelope of the soil of which point A is composed. Now let's go back to moving the wall out. The wall moves out a little more, maybe half a millimeter more, etc. And what you will get is a point in time that will cause the Mohr circle. These are very bad Mohr circles, sorry about that, but the idea is to draw a Mohr circle here that touches the envelope. It touches at this point. So what does this mean? This is very important and is also a source of confusion sometimes. So what this means is that this point, once the wall has moved out a certain amount, this point has a Mohr circle that touches its failure envelope, the soil's failure envelope. That means at that point is at failure because its Mohr circle is touching the failure envelope. Well, what does that mean? Well, that means that at a certain plane associated with this rotation right here, right? At a certain plane associated with this rotation, a certain plane over here, the shear stress has actually reached the strength, or it is actually now the strength. So there's a plane that crosses through this point on which the tau is S. And that's another way to say that is to say that the point is at failure along that plane. Again, what plane is that? We'll describe it, we'll find it later, but it is associated with the rotation associated with this line. Remember that we rotate like this? Okay, so we'll do that, we'll actually solve it later. What I want to make sure that you realize here is the following. Again, this point is at failure if the wall moves out a certain amount. the amount required for its Mohr circle of the point, to touch the failure envelope. Okay, now, is that a bad thing? No, that's not a bad thing, even though the word failure is in that sentence. When we say that a point in the soil is at failure, it doesn't mean that the system will fail. It doesn't mean that the wall is going to fall over. Okay? It means that the soil has reached along that plane a condition where it cannot provide any additional shear resistance. All the additional shear resistance has to be provided for by the wall. Let's turn this around so you can remember what we talked about before. The soil can sustain itself up to a certain point, but cannot sustain itself beyond that. It needs a wall for it to sustain itself beyond that point or beyond that slope. Okay? What we have said here is that this point is now at a condition where there's a plane on that point at which the soil can no longer, or cannot provide, any additional resistance to the resistance that it is providing, because it is providing the strength. It cannot provide more than the strength at this point on the plane in question. Which plane? The one associated with this rotation here. Okay? So where does this lead us? Well, let's now figure out what the K is for the case of this Mohr circle. This Mohr circle, the at rest one, the K was K0, which we calculate to be this. But for this Mohr circle, which is the special Mohr circle that touches the envelope of the soil, the K0, sorry, I shouldn't say the K0, I should say the K. The K is this horizontal stress, that one, which is lower than this one, obviously, right? Divided by the vertical. You have the same definition, just that the horizontal stress is different. The at-rest condition, for the at-rest condition is this value. For the Ka condition is this value. What's A? A stands for active. This is the active condition. This is the at rest. This is the active. This is the K active, because it is associated with that Mohr circle. This is the K0, which is associated with this Mohr circle. This is the lateral earth pressure coefficient, or the lateral stress ratio at rest. This is the lateral stress ratio in the active condition, also called active lateral earth or lateral stress ratio. Okay? Active. Which one is smaller? Well, if you divide this by that, you get a value. If you divide this, which is smaller, by that, you get a smaller value. So, oops, sorry. So this is what I wrote here, active condition, right? K active is smaller than K0. So again, in 462, you always used, that is in Geotech here at SDSU, you used K. That's all you used, K, K, K. Well, you were actually using K0. Now that we're in the world of walls, we have to realize that K can vary. It can be K0, it can be larger than K0, it could be smaller than K0. In this case, the smallest value possible, or in every case, the smallest value possible of K is K active. Okay, let me redraw the wall. Mohr circle at rest, failure envelope, tau, sigma prime, right? Mohr circle at rest, where the sigma horizontal over the sigma vertical is K0, right? Somebody's singing outside. Okay, and then there is the K active, or the active condition where the Mohr circle touches the envelope, right here. Here's the center of my circle, of my active circle. Active, at rest. Sigma horizontal, sigma vertical. Here's my point. Point A. Okay, so we're going to figure out what is that plane that is actually at failure. That is where the tau acting is actually S. Because remember that the equation of this line is S sigma prime tangent phi plus C prime, but this is 0. Because this is right here, right? There's no intercept. Okay, so how do we do this? Well, it's a Mohr circle problem, right? So if our point looks like this, sigma vertical, sigma horizontal, right? This one and this one. Remember, we're talking about the active case, obviously. Then what is it that we have to do? That is, what is the relation of the element, which is the point? This element is this point. What is the relationship between its rotation, etc., with the Mohr circle? Well, we know, that we rotated, or that we rotate this line here counterclockwise rotated counterclockwise an angle, let's call it theta, okay, such that we have this point. So we come from this point here all the way up to this one. We rotate theta. We rotated the line, the Mohr circle line, this one, counterclockwise theta degrees. This means that we have to rotate this element counterclockwise. How many degrees? Theta over 2. Because what we rotate in the field, we do twice with the Mohr circle. That's the rule with the Mohr circle, right? So, something you can see, okay. So then what happens? Well, let's take the element. We're taking this point all the way here. That's the point that has a sigma v on it. So we're going to shade this side. We have to rotate this element theta over 2. Okay? So if we rotate, if this is, let's kind of kind of eyeball what this angle is. This is 90. This is about 30. So that's like 120, right? This is like 120. So this is going to be more like 60. Or this entire thing, 120 divided by 260. Rotate the element 60 degrees counterclockwise. So basically we end up with .45, 60 is around here like that. This is theta over 2. So this is the plane where the tau is S, which is associated with that point. So if we draw this plane on this line, we end up with this. Or sorry, we draw this line across this point parallel, because we want the same one, right? We get that. Theta over 2. Perfect. So we know that along, or at this point, along this plane, the tau is S. What about this point? Well, if you were to draw the Mohr circle for this point, point B, this Mohr circle would actually be closer but smaller. It would still be touching. Okay, so the tau on that plane would also be S. What about at this point? Well, on that plane also tau is S. This point, tau is S. This point, tau is S. In fact, you would extend this line from the base of the wall all the way up at that angle, theta over 2, 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 right? And any point inside this wedge would be in the active condition if the wall actually moves out such that the Mohr circle for all these points touches the failure envelope. So all these points in here, inside this wedge provided by this boundary, which is slanted at theta over 2 and begins here at the bottom of the wall, any point in there, that is all points in there, are at failure. They are in the active condition, and they're in a situation where they cannot offer any more resistance than what they're offering to hold the soil up at 90 degrees. Okay? They only offer, remember, they only offer up to a certain point, which is their strength, basically the strength of the soil at those points on those planes, which is the same, basically, angled plane, right? The rest of the resistance, meaning the rest of the resistance that is provided to the system so as to create a vertical slope, is provided by the wall. Okay? So, where does this lead? Well, we have to actually realize that when we find the force that actually pushes the wall or could push the wall out and cause an actual failure, a system failure that we don't want, not a soil failure that is defined by this, but an actual wall failure where people can get hurt, etc., etc., we have to utilize this concept, because we have to realize that the lateral force or lateral stress is not sigma vertical times K naught in the case of a wall, because the wall has moved out and this condition of this active condition has been found. So this is not the case for a wall. The case for a wall is this one, K active. K active is the K that we use for wall design. Okay, now the question is, how do we get K active? We're gonna see how to get that in the next video, but something I want to make sure that you realize here is that, and is associated with that K active obviously, is the following. Look, this angle theta that defines the size of this wedge, right? Because we use this theta to rotate the element to then realize that this is theta over 2. This is theta over 2. So this theta, which dictates the size of this wedge, is a function of phi. How is that? Well, geometry, right? If the phi were higher, meaning this strength envelope were steeper, right? Then the Mohr circle would be larger. The theta would be different, a different value, but its relationship to phi would be the same. So there is a relationship between theta and phi because of the geometry that you see here. Just a circle and a line. The circle has an angle inside it associated with the center of the circle and a point on which it touches, or that coincides with the line, and the slope of the line is theta, or sorry, it's phi. So theta and phi are related, and therefore this theta over 2 is related to phi, and therefore the size of this wedge is related to phi. Okay, and that will be revealed later when we actually solve the geometry, or solve the system utilizing the geometry and arriving at this.